Hello, my name is Christopher DeLay. I'm a Senior Premier Field Engineer with Microsoft. Today I'm here to talk about Cryptography Basics. So this is a first course in a number of courses that talks about PKI. And before we get into some of those later discussions, it's important that we understand some of the fundamentals. So we're going to talk about cryptography here at a very high level, just so you have the basic understanding that you need to be able to apply to certificates later on. So what we're going to talk about is symmetric cryptography, asymmetric cryptography, what's called hybrid cryptography. There's other names for it as well, hash algorithms, and digital signatures. So first we're going to talk about symmetric cryptography. So symmetric cryptography is where there's one key that's used for both encryption and decryption of the data. If you're going to do encryption between two different parties, and obviously since it's the same key that's used for both of these processes, then you need to find a way to share that key between the two parties. Security is based on the key remaining private, which is true of most if not all encryption protocols. So the idea here is that we need to keep the key private, and only the individuals that need to do the encryption and decryption have access to those keys. And security is based on the sharing of keys through a secure channel. So we talked about there is the same key that's used for both encryption and decryption. And if there's two parties that are involved in this process, there needs to be a way for them each to get a copy of a key without it being compromised. So that's the issue that we have to deal with. Here are some of the characteristics of symmetric cryptography. So some of the advantages are that symmetric cryptography is fast, especially when compared to asymmetric cryptography, and generally requires smaller key sizes to provide the same level of security. For these reasons, symmetric cryptography is typically used for any sort of bulk encryption just due to the speed factor. Some of the disadvantages are there is no real built-in method for key exchange. There's no method for key management that's built in. And also that there is no method for non-repudiation. So the idea with non-repudiation is if I were to send an email to, let's just say, Alice, non-repudiation would prevent me from denying that I sent that email. And so that's a feature that's not available with symmetric cryptography. So key management is, like I said, a problem with Kerberos. And the idea here is, in this example here, you can imagine an environment where you have 100 users. And if they were going to use symmetric cryptography to securely communicate with each other, each one of those users would have to have a unique key for each other person they were having a conversation with. So you would have a lot of keys. In fact, you would have roughly around 5,000 keys if they were all sharing information with each other and trying to do that securely with symmetric cryptography. So that can be a problem. There are some solutions. So if we look at Kerberos uses symmetric cryptography, but it does a good job of handling keys. There's long-term keys in terms of passwords, and there's shorter keys that are used for different authentication sessions. So Kerberos definitely does do this. So Kerberos uses a key distribution center to handle most of this work, and Kerberos does maintain the long-term keys, which are passwords, right? Passwords for the machines, passwords for the users, that sort of thing. And Kerberos creates session keys for users when they're attempting to authenticate to either the domain or to different services in the domain. So again, just an example that Kerberos can handle this key management aspect. Some examples of symmetric cryptography are here, some different sort of algorithms. The most common one you typically see is AES, right? Some of these other ones you may not have heard of, but AES is a pretty common one. Here's an example of symmetric cryptography just to kind of illustrate how everything works. So in this example, Bob wants to encrypt data so that he can send the data securely to Alice. So what he does is he gets a copy of the data that he wants to protect. He then gets the symmetric key and then encrypts the data with that key. Bob then sends that encrypted data to Alice. And then Alice uses the same key, which she has a copy of, to decrypt that data. And then she can now read that data. So that's just a quick example showing how symmetric cryptography works, just to kind of make it maybe a little bit easier to understand. So next we're going to talk about asymmetric cryptography. Asymmetric cryptography is important because it gets into the public and private keys that we're talking about with certificates. So having at least a cursory understanding of this is helpful. So asymmetric cryptography is based on two keys. Those two keys are related, right? The public key is made available to the world. You can make the public key freely available. You don't have to really be that concerned with securing it. And the private key is kept secret. Now, it's very important that you keep that private key secret. And that's handled in different ways. Sometimes it's stored in hardware. Sometimes it's protected by, software encryption. So there are various ways to do that. But the main point is that the private key needs to be kept secret, because if that key is compromised, and obviously people will be able to compromise data, spoof signatures, that sort of thing. So it's important to keep that private. Data encrypted with the public key can be decrypted with the private key, and vice versa. So again, if you encrypt something with the private key, it can be decrypted with the public key. If something can be decrypted with the encrypted with the public key, then it can be decrypted with the private key. So there is a relationship in terms of encryption there. And security is based on keeping the private key secure, which we kind of talked about already. And then there isn't a security aspect that's based on able to identify who's associated with that key, right? If we just have keys floating around and we don't really know whose key is whose, it's kind of hard to without that association, it creates some sort of problems for security. And so if you're able to associate an identity with a public key, that's definitely helpful. And that's kind of what certificates do, right? They bind that identity to a public key. So here are some characteristics of asymmetric cryptography. So some of the advantages are that asymmetric cryptography typically supports key agreement, which is basically two individuals coming to an agreement on a same symmetric key. And there's protocols like Diffie-Hellman that allow users to do that over an insecure network. And there's key exchange. Key exchange allows you to basically share a key over an insecure medium. And then another advantage is non-repudiation. So I gave a quick example earlier. If I send an email to Alice and basically if I sign it, which we're going to get to signatures a little bit later on, if I sign that email and send it to Alice, I can't deny that I sent it, because through cryptography and hash algorithms, Alice can prove that I was the one who sent it. Some of the disadvantages are that you'll see key sizes for asymmetric cryptography are pretty large. Like RSA keys are typically around 2K or 2048 bit. So that's a large key size compared to asymmetric cryptography, where we're talking AES is usually 128 or 256. There are some elliptic curve cryptography, which is more efficient in the sense that it uses smaller keys and it requires less computational power. So there are some protocols, some different protocols that have been developed to sort of deal with some of those problems. And the other disadvantage is that it's computationally expensive. Since it's involved with the factoring of large prime numbers, it requires a lot of processing power to create these numbers and to do all this mathematic work. So it's going to be much slower than symmetric cryptography. Here's like some examples of asymmetric ciphers. Diffie-Hellman is a common one we see for a key exchange, and RSA is one we typically see used in certificates. And the last two are elliptic curve DSA and elliptic curve Diffie-Hellman. Now these are protocols that are going to typically be used on devices that have limited processing power. Here's an example of asymmetric cryptography. So in this example, Bob wants to encrypt data so they can send the data securely to Alice. So Bob retrieves a copy of the data that he would like to protect, and then he must retrieve a copy of Alice's public key. So the question is, where does he get that public key? So it may be stored in different places. Of course, this is the one sort of difficult thing with asymmetric cryptography. How do we share that public key? If you go to a website, the public key is on the certificate that's on that website if it's protected by TLS. In an enterprise environment, it can be stored in Active Directory on the user certificate attribute. In Exchange, there's certain places where it can be stored. You can have that person's key in their contact in Outlook, so there are some different places to get it. So Bob retrieves the key, and then he, with that key, he encrypts the data. He encrypts the data with Alice's public key. In real world, we wouldn't necessarily be using asymmetric cryptography for bulk encryption, but just for this illustration here, we're just going to say that Bob actually does the bulk encryption with Alice's public key. Bob then sends the encrypted data to Alice, and then Alice decrypts the data with her private key, which only she has access to. And then Alice can now read the decrypted data, and she can access it. So hybrid cryptography is just, there's other names for it, but this is just an example of taking two types of cryptography and creating sort of a better solution, right? So the use of two crypto systems for a complete crypto solution. Symmetric cryptography is used to encrypt data or do bulk encryption, and asymmetric cryptography is used for key agreement or key exchange. So we see when we use these two things together, we get sort of the advantages of each. So we have the speed and smaller key sizes that symmetric cryptography has, as well as the lower computational overhead compared to asymmetric cryptography. And then with the asymmetric cryptography, you have a way to exchange these symmetric keys, to either exchange them or come up with key agreement. And there's some other things we can do, and we'll see some of these other things a little bit later. So here's an example of hybrid cryptography. So Bob retrieves a copy of the data he would like to protect. Bob creates a symmetric key. Again, this is the same key that's going to be used for encryption and decryption. Bob encrypts the data with that same symmetric key that he just created. Then Bob goes and retrieves a copy of Alice's public key. Again, he may get that from different places. Bob then encrypts that symmetric key with Alice's public key. So again, the data is encrypted with the symmetric key, and in this example, the symmetric key is encrypted with the asymmetric key, if that makes sense. So Bob sends all this information over to Alice, and then Alice basically decrypts the symmetric key with her private key, which only she has access to. And she now has access to that symmetric key, which she can use to go ahead and decrypt the data. And then now Alice can read the decrypted data. So this is one way which both of these symmetric and asymmetric cryptography can be used together. Obviously, in real-world applications, things may differ a little slightly here, but just to give you the general idea of how this may work is the purpose of this example. SSL is an example of hybrid cryptography where both symmetric and asymmetric cryptography are used. Here's a Microsoft KB that discusses how the SSL handshake happens, and that kind of shows you how the different types of cryptography are used. Obviously on websites now we use what's called TLS, not SSL. A lot of people still refer to TLS as SSL, but just be aware that there is a difference. Hash algorithms. So next we're going to talk about hash algorithms. So hash algorithms create a fixed length output out of a variable length input. So what does that mean? So that means I could put a very large document, let's say hundreds of pages, through a hash algorithm, and I will get, I'll get a output of a certain size. Now, no matter what type of document or material I put through that hash algorithm, I always will get that fixed size, whatever that may be. That output is then called the message digester hash. So those are just two different names for it. The algorithm should avoid collisions. So what does collisions mean? Collisions is when you have two different inputs that end up having the same output. So that can cause a problem because, especially if you can predict, if you can control what the inputs are and get the same output, right? Because you could have for example, you could have a contract that's signed, and then if you are able to alter that contract and still get the same hash, which would result in the same signature, then that could be a problem. So these hash algorithms should avoid collisions. There's been issues found with many of the older protocols. So, MD5 obviously has this issue, and SHA-1 has been shown to have this issue. So those are kind of not really considered secure right now. So these are things that you should not be using. Hash algorithms are used in conjunction with public key cryptography to create digital signatures, and we'll see an example of that shortly. Here are some examples of hash algorithms. Again, we have MD5 and SHA-1, which are sort of insecure at this point, and then we also have what's normally used now in certificates is SHA-2. And there's There's a number of variations of SHA-2. I think there may be another one in here that's not included, but the ones you typically see are SHA-256, SHA-384, and SHA-512. In real-world environments, we typically see SHA-256 typically used, just because there's usually a feeling that may be more supported between different applications and hardware and services, but there are these three different options that are available to you. So next we're going to talk about digital signatures. Digital signatures leverage both asymmetric cryptography and hash algorithms, and we'll see how that works here in a second. So digital signatures provide two functions, right? So one is they provide authenticity of an email or document. So what does authenticity mean? So authenticity means basically a couple different things depending on how you're looking at it. But the main thing I would be thinking about here is that it's a way to prove that the document has not been altered since it's been created, right? So that's kind of the important thing. I create a document, I sign it, I send it to Alice. Especially if it's a very important document, Alice may want to be able to know that that document has not been altered in transit or by a malicious person. And so digital signatures provide that capability. And then digital signatures can also provide non-repudiation for an email or document. And kind of like we've talked about a couple times already, basically the idea is if I send an email to Alice and I sign it, I can't deny that I sent that email because through the digital signature, she can prove that it was signed by me. So these are some of the capabilities or features that are provided by digital signatures. So here's an example of a digital signature. So in this example, Bob has a document that he would like to sign. So let's just say a Word document for the sake of this discussion. Bob then takes that document and runs it through a hash algorithm. We talked about SHA-1 being insecure, but this is just for the purpose of illustrating this. It's not that important. This is mainly just to understand the process. So Bob takes the document and he basically runs it through a hash algorithm and he gets his hash or message digest, right? A fixed length output that should be, unique between different things that could be put through the process. So anyways, he ends up with his message digest or hash. Bob then takes that hash and encrypts that hash with his private key, creating a digital signature. So now he has this digital signature of the document. So he has a document and he has the digital signature. So he sends that document along with the digital signature to Alice. So Alice gets a copy of the document and the digital signature. And then Alice is going to go ahead and run that document through the same hash algorithm that Bob did. So there's going to be some metadata in the document that indicates that he used SHA-1. So she's going to get that metadata, figure out that it's SHA-1, and run the same document through the SHA-1 algorithm, and she's going to get a hash or a message digest, as we can refer to it either way. And then Alice goes ahead and gets that digital signature and decrypts it with Bob's public key. So remember, there's a relationship between the public and private key. Since he encrypted something with his private key, it can be decrypted with the public key. Again, how she got that public key, that can happen in a couple different ways. It could likely be included in a certificate that's attached to the signed document. So there's different ways that can be distributed. So at the end of the situation, Alice has decrypted the digital signature with Bob's public key. And then Alice compares the hash she generated with the hash that was decrypted with Bob's public key. So here's a couple things that we find out. So if the hashes match, we figure out that the document hasn't been altered in transit, because otherwise the hashes would not match, right? If somebody changed some words in the document or anything in the document, the hashes would not line up. And then the other thing is, since she was able to decrypt it with Bob's public key, she knows through the cryptography that Bob had to encrypt that hash or message digest with his private key. So she knows that it's Bob that actually signed this document. So she can prove two things. One, that data has not been altered, and that it was Bob that signed this document. And here's just a quick illustration just for better understanding of how this process works. And so that ends this talk. There will be some other talks on various different topics, and we're going to get deeper into PKI. The next talk, we're going to talk about certificates, and we're going to talk about the structure of certificates, what information included in certificates, and some more on that. Hopefully this information was helpful to you, and I'll see you next time.